In this video, we will discuss addition and subtraction of vectors, multiplication of a vector by scalar, and scalar or dot product involving vectors. Suppose you're given two vectors, a and d, and you want to add them, like shown, a plus d equals the third vector v. So let's start with the first vector, vector a. So that is vector a. And then followed by vector d, go like that. We connect now the tail of a to the head of vector d. And that is vector v. Another example, g plus h equals to s. Again, you begin with vector g, followed by vector h, and to obtain vector s, the result of the sum, you connect the tail of g to head of vector h. Like that. And that is vector s. Next, let's do subtraction. Let's say you want to subtract vector d from a. So a minus vector d is vector c. So how do we represent the subtraction? Well, first, let's rewrite the left-hand side of this vector equation in the following manner. So a minus d is a plus minus d. Now, if d is, as shown, minus d is a vector that goes anti-parallel to d. So this is minus d. So now the sum is as before. We have turned the subtraction to a sum. So we go with a first. So that's vector a, followed by vector minus d. And again you connect the tail of a to the head of minus d. And that is vector c. Simple as that. Next example. Let's say we want to subtract g from h. So h minus g equals to, let's say, vector l. So we rewrite the left-hand side of this vector equation in a form of sum, so that we can use the method that we use for sum here, and realize the fact that if g is as shown, then minus g is a vector that is anti-parallel to the original vector g. So we start with vector h, followed by minus g. So minus g is going this way. And you connect the tail of h to the head of minus g. Like that. And that is vector l. So far we have add and subtract vectors graphically. So they are not to scale, just to give you a qualitative understanding how to carry out sum and subtraction. Now next, we shall look at how to add and subtract vectors more accurately using unit vectors. So you're given three vectors, generic vectors in terms of unit vectors, f, e, and g. And you want to, let's say, sum e and f. So how do we do this? Now you sum I with I, j with j, and k with k. That's how you do it. So the I will go with this I, so 2 plus minus 3i, so that's going to give you minus I hat. This j will go with this j, so minus 4 plus 3, so that's minus j hat. And finally k with k, that's 3k hat, and that's the sum. So that means your answer is minus I hat minus j hat plus 3k hat. And that is the result for this sum. Let's look at a subtraction. The same thing. F minus E, so minus 3i minus 2i, so that is minus 5i hat. 3j minus minus 4j, so that is 7j hat. And k minus 2k, so that is minus k hat. So meaning the answer is minus 5i hat plus 7j hat minus k hat. So that's the result for the subtraction. Now you can add the operations like shown here. So let's see how to do this. Again, you stick I with i's, j with j's, k with k's. So I with I, so I minus 3i, that's 4i. 4i plus 2i, so that is 6i hat. Minus j hat minus 3j hat, so that's minus 4j hat. Minus 4j hat minus 4j hat is minus 8j hat. Minus k hat minus k hat, so that's minus 2k hat. Minus 2k hat plus 2k hat, that is 0k hat. Meaning the answer is 6i hat minus 8j hat. So you don't have to write the 0k hat. Next, let's look at scalar multiplication. Now if you have a vector, let's say vector A that goes like this. Now you want to multiply 2 to this vector A, the positive scalar. So how does a vector 2A look like? So it will point in the same direction as vector A, but now it will have a magnitude twice that of A. So 2A would look like this. So this is vector 2A. Another example, if you have a vector W as shown, now I want to know how to sketch vector half W. So vector half W is parallel to vector W, but it would have a length which is half that of vector W. So this is vector W, half W. Multiplication by a negative scalar. Suppose you have a vector E as shown. Now you want to sketch a vector which is minus 2e. So minus 2e will point in a direction opposite to that of e, but it will have a magnitude twice that of e. So it will look something like this. So that is vector minus 2e, and so on. So if you multiply this vector e with, let's say, minus half, then it will result in a vector that is antiparallel to e, but with a length half that of vector e. Let's now look at scalar or dot product of two vectors. So what is the definition? Now if you have two vectors that look like this, so this is vector A, and this is vector B, and the angle between the two vectors is, let's say, theta, then we can define a scalar product or a dot product between A and B according to the following definition. So A dot B equals the magnitude of vector A times the magnitude of vector B times cosine of the angle between the two vectors. Now we can note from here that if you have two mutually perpendicular vectors, let's say a C vector and a vector D here, and the angle between them is 90 degrees, then the dot product of two mutually perpendicular vectors, such as C and D, will be 0, because cosine 90 is 0. Another thing to note is, if we reverse the order of vectors in this dot product, so B dot A, for example, it will become the magnitude of B times the magnitude of A times cosine of that same angle, theta. So we see the right-hand side of A dot B and B dot A are the same, because these two terms are the same. Now that means A dot B equals B dot A. So the order of vectors in dot product does not matter. They commute. Next, let's try to calculate dot product among unit vectors. There are 3 unit vectors. So the unit vectors along the x-axis, the I hat. The unit vector along the y-axis, j hat. And the unit vector along the z or the z-axis, k hat. So let's begin with I dot j. So by definition, I dot j is the magnitude of I times the magnitude of j times cosine of 90, which is 90, because 90 is the angle between them, and that's going to give you 0. Now you can calculate the dot product between, say, j and k. For the same reason, they will vanish. Likewise, I dot k will also vanish. Now what about dot product between I dot I, between I and I? Now from definition, this should give you magnitude of I hat times cosine of 0, because they are considered to be two parallel vectors, and you get 1. So the same thing holds for j hat dot j hat, that's 1, and k hat dot k hat, which is also 1. Now we can use these results to calculate dot product between any two generic vectors, such as the ones shown, a, b, and c. Let's look at the following dot product, a dot b. So we do term by term. I dot j, that's 0. I dot k, it's also 0. J dot j, that's 1. There's a minus 3 there, so it will give you minus 3. J dot k, that is 0. K dot j, that's 0. And k with k, that's 1. That's a minus 4 there, so it's going to give you a minus 4. So the final answer is minus 3 minus 4, which is minus 7. Another example, a dot c. So here, I dot I, that's 1. So there's a minus 1 there, so it's minus 1. I dot j, that is 0. I dot k, that is 0. Now j dot I, that is 0. J dot j, that is 1. And j dot k, that is 0. And finally, k dot I, it's 0. K dot j, that is 0. And kk is 1. There's a minus 4 there, so that is minus 4. So the final answer is minus 1 plus 1 minus 4, which is minus 4. Next time, we will talk about cross product, or the vector product between two vectors, and conclude our discussion on vectors. Until then, thanks for watching.